Miniemulsion polymerization. It's a subclass of polymerization in heterogeneous media or in dispersed media. You have in your welcome package a nice review on the different techniques that use the dispersed media approach to do polymerization. There's many different advantages of doing polymerization in dispersed phase. When you're talking about thinking of free radical polymerization, for example, if you do a polymerization in bulk, this reaction is really exothermic, and then we need to find ways to improve the heat exchange to have a controlled polymerization process, and then going to a dispersed phase, it's a really efficient way to do that. There's other advantages as doing polymerization in the dispersed phase, and one of which is to go toward more environmentally friendly type of material processing, because using dispersed phase, usually we decrease the amount of volatile organic compounds that are generated during our reaction. And that's also something that we like, and today I will talk about all the reason why we should love mini-emulsion.
That's great. How did you manage to get these images?
Luck, serendipity. Yeah. So one of the most attractive feature of mini-emulsion polymerization compared to maybe all the other polymerization type in dispersed phase is that mini-emulsion polymerization is very versatile. It's versatile with the different type of monomer that we could use. We could use styrene, we could use acrylates, we could use very hydrophobic monomers, we could use very hydrophilic monomer to make gels. We could also use different type of polymer, and then with those polymerization, we could really finely tune the size of those particles. So using styrene, we are able to make very small or relatively small particles, and to control the size of the particle just by controlling the condition at which we do the emulsion and the different component that we add to the reaction. It's also versatile in terms of which type of polymerization we could use. The first one here is just making copolymers. So other types of polymerization in dispersed phase, it's really difficult to have well-controlled copolymer structure, because to some extent they are reliant on the diffusion of the monomers through the continuous phase, which lead to gradient in composition or to inhomogeneous composition. While mini-emulsion polymerization, it's probably one of the best way in dispersed phase to get well-controlled copolymer structure. And it's also compatible with different polymerization process, whether it's raft, ATRP, anionic, cationic, and all kinds of different cross-coupling, from Sonok-Goshira coupling to make new carbon-carbon bonds, or to thiolene, or the addition of an azide with an alkene. All those things, types of reaction have been done in mini-emulsion, and basically most chemical reaction that we could do in bulk could also be done in mini-emulsion in some way or the other. Another very interesting feature of mini-emulsion for me is that we could encapsulate things. We could encapsulate small molecules, and we could encapsulate particles. We could encapsulate smaller polymer particles and bigger polymer particles. We could encapsulate magnetic iron oxide and polystyrene. We could encapsulate a variety of different organic and inorganic compounds. And the efficiency of encapsulation using mini-emulsion is unmatched by any other polymer-based technology. It's also versatile in type of shape that we could make. We could make spheres, yes, but we could make Janus particles. We could make core shell, or core shell, or mini shell structure. We could make empty nanocapsules, and we could play a little bit with the shape of the particles that we make. For different application, it might be of interest sometimes. So before proceeding with the presentation, I would like to give you some definitions. Sometimes I use the words, not the right word for the right situation. So some words that I will be using today will be like a colloidal system. It's just a system where you have two discontinuous phases. You have a continuous phase where you have another phase, the dispersed phase, that is dispersed inside the continuous phase. And usually there's this dispersed phase will be on the order of several nanometer to several micron. A dispersion, it's any two phases that are dispersed in one another. And an emulsion, it's a liquid in another liquid. So we don't have an emulsion of nanoparticles. We have a suspension of nanoparticles, which is a solid dispersed in a liquid. However, a colloidal suspension, it's not solid particles that are of colloidal size. It's just anything that is, any colloidal system could be referred to as a colloidal suspension. So those definition comes from either the UPAC Gold Book, so you could find that on the internet, or the most recent IUPAC recommendation for the terminology of polymerization in dispersed system that dates back now from 7 years ago. So there's different kind of something emulsion polymerization. So today I will talk about mini-emulsion polymerization, but before mini-emulsion polymerization, there was just emulsion polymerization. That's the grandfather of mini-emulsion polymerization, if you will. So in emulsion polymerization, you have the components that you have is monomer, a surfactant, and a continuous phase. The monomer needs to be insoluble in the continuous phase, and you need an initiator that will be soluble in the continuous phase. The size of the nanoparticles that we end up with during emulsion polymerization will be somewhere between 50 nanometer to maybe 1-2 micron. And we use a surfactant, and the surfactant needs to be used above the CMC, the critical micellar concentration of the surfactant, which means that the surfactant before the emulsion is present in the form of micelles. So before the polymerization, there's a separation, the segregation of the monomer phase that is immiscible with the continuous phase, either inside the micelles or inside bigger reservoirs. And we have some empty micelles too. And during the polymerization process, the monomer that are insoluble in the continuous phase, but nothing is really insoluble. They will slowly diffuse through the continuous phase, react with the initiator molecule in the continuous phase, and just statistically enter one of the micelles that contain or not some monomer, and then the reaction, the polymerization reaction will progress. And it's just statistical that we don't polymerize the bigger reservoir, because the surface area of the small micelles is much larger than the surface area of the bigger reservoirs. But anywho, at the end of the polymerization process, we end up with nanoparticles that are more or less homogeneous in size. Then in the mid-80s, early 90s, what was the process that was very popular was microemulsion. So someone decided that emulsion, the particle size is too big. How could we decrease the size of the particles? So in microemulsion, we use, again, a monomer, a surfactant, and the continuous phase with an initiator. But also we need, it requires the use of a co-surfactant. And in this case, usually the initiator is also in the continuous phase, but sometimes there are some cases, rare cases, where the initiation could take place in the dispersed phase. So at the beginning, we use very high concentration of surfactant. And when we increase the surfactant above a certain threshold, we don't have micelles anymore, but we have more liquid crystalline phases. And there's a network. Either it's very concentrated micelles that are almost touching, or we could also have a bicontinuous network of those liquid crystalline phases that contain the monomer. And then slowly we will add the co-surfactant. This will destabilize the system and will trigger the formation of very small micelles. And then again, through diffusion of the monomers through the continuous phase, we end up with nanoparticles after polymerization. And the size here is really small, usually between 10 and 50 nanometers, sometimes even smaller. Then a little bit after the microemulsion, mini-emulsion became really the way to transfer those disperse phase type of reaction to a process that could be scaled up and that is really interesting for the formulation of latexes for paint and other industrial application, because it's a little bit more stable, I would say, or less complex. The dynamic of the system is a little bit less complex. In this case, the components are once again the monomer and the continuous phase that are immiscible together. We use a surfactant and we use a new component, the osmotic pressure agent. I will discuss about what it does exactly a little bit later. And the initiation could be either in the continuous phase or in the disperse phase. Either are good as the other. It really depends on your system, on the solubility of the monomer in the continuous phase, on the kinetic of the reaction that you want to achieve, and so on. So there's no rules of where to put the initiator, really. And we end up with sizes that are similar to what we observe with emulsion polymerization. However, we use much less surfactant. But because we use much less surfactant, the formation of the micelles or of the reservoir of monomer is not spontaneous. We need to give energy to the system to break down the disperse phase in small droplets that will be stabilized by the surfactant. And although it's sometimes up for debate if we could really say that every reservoir that we form with the droplets of monomer that we form is exactly transfer into one particle, it's usually understood that we will end up with as many nanoparticles as we have of nanodroplets. So that's an overview of the different emulsion polymerization techniques. Sometimes mini-emulsion could also be referred to as nano-emulsion, but it's not so much about a different mechanism, it's just to highlight the size. The term mini-emulsion, it's not mini. Micro, it's 10 to the power minus 6, it means something. Mini, so if we look at the mini-emulsion, the different steps, so we mix two phases. We have a water phase contain usually water, a surfactant, and sometimes we could put the initiator there. We have the oil phase, so when we say oil, it's not because we use oil, it's just anything that is not miscible with water, we call it oil. So it's composed of monomer. Sometimes we will have a co-solvent, we have a osmotic pressure agent, and we could put the initiator there. And then there's this critical step of homogenization. So we could use ultrasound, we could use different modes of homogenization. Usually we'll have form a pre-emulsion just by stirring the biphasic mixture for a while, just with a magnetic stirrer. We could use a ultrathorax, which is a rotor stator type of device, but at some point we need a lot of energy, and this energy, most of the time in the lab scale, will be from ultrasound. And then we need to initiate the polymerization. In this project, it would be with light, but it could be with temperature, it could be by the addition of a reactant, of a catalyst, and so on. So if we look at the samples, so if we have our two-phase system, after homogenization, the transparent samples are transformed into an opaque sample. That's because we form droplets that are hundreds of nanometer, which is this, the range of, is in the range where the particles or the droplet will scatter light, which cause this, this opacity of the sample. And so the key step is ultrasonication. So here it's a sample being ultrasonicated. So we could see that there's a lot of things going on, and I will try to go through the different process involved there. So just sometimes you will hear something about Miniemulsion and then inverse Miniemulsion. It's exactly the same thing. It's just, again, historical nomenclature. So the Miniemulsion is usually for oil and water emulsion, and inverse Miniemulsion is for water and oil emulsion. But basically it's the same thing. We use different surfactant and we use different osmotic pressure agent, but the principle and the reality of it is exactly the same thing. So the key step is really how to form this Miniemulsion. So we could use different device. We could use a rotor-stator mixer, which is basically just like the stick blender that you might have at home, but with a slightly higher rotation speed. We could use high-pressure homogenizer, where pump will push at very high pressure the pre-mix system into interaction chamber. This interaction chamber could be different things. Could push through a very narrow channel, could push into a different channel that will create impact, and then you have a combination of shear that will break the droplets, of cavitation, of impact force that will lead to the formation of the homogeneous, well, not homogeneous, of the uniform droplets. Those two processes are usually the one that are used to scale up the production of Miniemulsion. And then there's also membrane emulsification that we have. It's a process that we have borrowed to the field of liposome and of making vesicle, whereby forcing our our mixture of monomer through a membrane, we form small droplets in the continuous phase. So we could either do the emulsification directly of just one phase into the other, or to push the mixture through the membrane. And then there's ultrasonication, which is our favorite in laboratory in academia. So if we look at the ultrasonicator, that's the ultrasonicator that we recommend, I think. It's the Branson. It works at 20 kilohertz. So there's the interesting parts are here. So we have the converter, we have a horn, and then we have the tip. So if we look more precisely to the different part of this ultrasonicator, so we have the power supply. The power supply is just there to convert the power that we get from any electrical outlet at 60 hertz into to modulate it instead at 20,000 hertz or 40,000 hertz, depending on the ultrasonicator that you're using. And then we have the converter. That's the top part of the ultrasound stick. It's in fact made of a piezoelectric actuator. So a piezo is a material that when you apply a difference of potential will either contract or expand. And this cyclic expansion with the frequency of the electrical power that is applied to it will convert the electricity into an oscillating movement. The oscillation at the end of the piezo is about 2 to 5 micrometer, depending on the model that you use. Then we have the horn, or the booster. So it's used to amplify the movement of the piezo. So it's designed to be a fraction of the wavelength of the oscillation created by the actuator. So you cannot really mix and match the booster from your 40,000 ultrasound with the one with the 20,000. It doesn't work. It's really designed for a specific frequency and wavelength of oscillation. And then we have the tips, or the sonotrode, that will finally transmit and also amplify your oscillation to your sample. It's usually made of titanium, sometimes of aluminum. One thing is that it doesn't oscillate laterally. It oscillates up and down. And depending on the amplitude of the power of the frequency and the material and the mass, the size of the sonotrode, you could have oscillation that will vary between 20 micrometer to 50 micrometer. So we could see that it's not really, if we have a big beaker containing 10 milliliters or 20 milliliter of solvent, it's not this little, only this little oscillation that will create the mixing that we need to break the droplets. It's much more complex than that. So here we have our tip that is oscillating. In the solution, what it creates wave in the liquid of different density. And so we have points of low density and points of high density. And in spaces of low density, we could either, because there's already an air bubble passing by, or just because of the effect of the oscillation itself and the difference of pressure, create a cavity. This cavity will be filled with water vapor if we use a water phase. And then in the zone of compression, this bubble will shrink. And then in the next zone of depletion of concentration, it will expand again until it reaches a critical point. And at that point, it will implode. This implosion will create first of all, very high local heat. It will create high pressure. But what is maybe more interesting for us is that it will create very rapid liquid jet streams and a turbulent flow. So those cavitation events are really what we need to create the emulsion. And those cavitation events are more frequent, very close to the tip of the probe than far away. So if you're just, if you're at few microns from the tip of the probe, you might have hundreds of cavitation events per second. But only 1 centimeter away from the probe, it will be less than 1 cavitation event per second. So the efficiency of mixing created by those cavitation bubble bursting is really localized to the region very near the tip. But fortunately, it also creates turbulent flow that could be used to mix the sample, or we could mix the sample using stirring during the ultrasonication alternatively. So why do droplets break up during sonication? First of all, those jet streams, they could create impact between two droplets, but it also creates very strong shear force. So if you elongate a droplet because you're shearing the droplet, it will first deform, it will deform more, and at some point it will reach a breaking point, and then you will have 2 smaller droplets. This breaking, deformation is breaking could be predicted by the capillary number of the system. It's not a perfect description for the complex physics of the cavitation itself, but in a simple shear experiment, we could really see a relation between the interfacial tension of the droplet and the viscosity of the continuous phase and the shear force, the shear rate that is applied to the system. And we could find a region where we only have deformation that will be reversible, or if we applied bigger shear, or if the interfacial tension decreases, we could end up with really breaking up the parent droplet into two daughter droplets. And so if we look at the ultrasound again, so the white spots that we see moving, it's not really the bubbles that are formed during cavitation, but it's the consequence of the bubbles that are formed. The bubbles that we are forming with a sonotrode working at 20 kilohertz will be about 150 micron in size. And the effect, so I mentioned the frequency, because the effect of frequency is the higher the frequency, the smaller the bubble will be. But you will also be making more bubbles. But because the bubble is smaller, when the cavitation happens, it will be, it contains less energy. So there's a trade-off between having a lot of low energy bubbles or having a few high energy bubbles. And at the end of the day, if you sonicate your sample for long enough, you will reach more or less the same steady state condition, but it will take different time, and it might not be exactly the same equilibrium that you will form. Yeah. So what is really important is the amplitude of the movement. And this amplitude of the movement, it depends a lot on the mass of the tip. So if you use different tips, if you use the half an inch tip as here, or if you use the quarter-inch tip, the amplitude of the movement is different. And then the energy that you have in the sum of the cavitation event that you observe will be much different. And then scaling the sonication time with different sonotrode is a little, it's not trivial, and you just really need to try a range of different conditions if you want to really change the sonotrode. So we don't only have cavitation during sonication, we also create turbulent flow, which could be used to mix. So here I'm mixing some large particles of agarose and water, and so just when the ultrasonication is applied, it creates turbulent flow. We could map those turbulent flow. The mixing is really good by using only the turbulent flow that are created from the ultrasound, but this could also be improved or complexified if you put a steering magnet at the bottom and then steer your solution during ultrasonication. The flow pattern becomes very more complex and more difficult to predict. It depends a lot on the size of the vial that you use. So those flow patterns, they are reflected by the walls of the vial. So if you use a vial that is bigger, that is wider, those turbulent flow will not be as efficient to induce mixing. So if you only want to use the turbulent flow created by the ultrasound probe for your mixing, you should have a very narrow vial that is very tall, more than a wide vial that is not that tall. So yeah, you have both breaking of the droplets, but you also have collision between droplets that are induced by those turbulent flow. And we could really see the fission of different droplets by mixing different solutions. So here we have iron chloride in one emulsion, and iron hexacyanate in the other one. And then if you mix those two stable droplets together, you just have a mixture of different droplets with nothing is happening. But if we applied ultrasound to the system, then we observe a change in coloration, because there's the reaction between the iron chloride and the iron cyanate to make a diiron hexacyanate that is colored blue. So we could see that by applying ultrasonication for just a little bit of time, it induced collision between those two droplets, two types of droplets that are mixed together. And then we could have reaction between components that are encapsulated in different droplets. So yeah, we have we break droplets, we collide droplets, we form new droplets. It's very complex what is going on in the ultrasonication. But what we want to do is to reach at some point a steady state where the droplets that we have are not changing anymore, that we always have the same number of droplets that are have more or less the same size. So what was done here is emulsion of styrene and water, and the emulsion process was could be monitored by many different ways. But here it's monitored by turbidimetry, just to look at how opaque the system is, and by surface tension. And here it's not measured by the size of the droplet, because it's actually very difficult to measure the size of the droplets, because it's not necessarily very thermodynamically stable. And to measure the size of the droplet by light scattering, for example, you need to dilute your sample. And by diluting your sample, because it's too concentrated for light scattering when we do mini emulsion, you're changing the position of the equilibrium, and it could change the size. So directly measuring light scattering of dilute solution, the size that you measure is not exactly what is in the emulsion. Other techniques could be used to measure the size of the droplets in the mini emulsion, like small angle X-ray scattering, but it's not a technique that we have available in all the labs, and it could be done once to see it, but not on a regular basis. Measuring the change in surface tension is for us the most convenient way to really track the process and to make sure that we reach this steady state. Usually it will take between 10 to 30 minutes of emulsion at high power, at high amplitude, to reach this steady state. But what we could do is to rapidly, after the emulsion, polymerize the particles, and then we could dilute them and measure the size, and then we could measure the particle diameter that are formed for different sonication time or different amplitude. So if we keep the amplitude constant and increase the sonication time, we see that at some point we reach more or less the equilibrium. If we fix the sonication time to 20 minutes in this case, and increase the amplitude, the same thing is observed. The problem is that if you stop your sonication at a short time, or if you use very low amplitude here or there, you're not in this region where the size of the particles is not changing anymore, which means that to do the sonication for 2 minutes or 2 minutes, 5 seconds, and if the amplitude change a little bit, or if any other factor, if the ambient temperature change, it will change the results that you get. While if you really reach this steady state, then it will be reproducible from one emulsion to the other. Yeah. So now the problem that we have with the mini emulsion is that the droplets are not that stable. At some point, I use ultrasound, I form my nice emulsion, but if I wait for a day, the system goes back to the two-phase system. So in this vial, I only emulsified water and the monomer phase containing a dye, but yeah, a very simple system. So we could see the mini emulsion is not stable. So to stabilize, we could add a surfactant. It helps a little bit, but still it's not perfect, because there's still a biphasic mixture. We still have a little bit of emulsion, and it's a complex system. If we really want to keep the stability of the droplet for a while, we need also to add both the surfactant and the osmotic pressure agent. So first, we'll talk a little bit about the surfactant. So a surfactant, it's a molecule that is a surface active agent, hence the name. And when you add a surfactant molecule to a solvent, many different properties of the solution will change. And the surface tension will decrease, and if you use an ionic surfactant, the conductivity of the solution will increase. If you probe the surfactant molecule itself by NMR spectroscopy, for example, the relaxation time will increase when you reach a critical concentration that is called the critical micellar concentration, where at this point, the surfactant molecules, so they are surface active, they really like to be at the interface between water and air, or between two liquids. If you slightly increase the concentration, you populate this interface a little bit more, but you have more and more surfactant molecules in solution, and at some point you reach a concentration where the interface is completely covered by surfactant molecules, and you start forming micelles inside the solution. So the effect of the surfactant on mini-emulsion, or the stability of droplets, it's because it reduced the interfacial energy. It's reduced the surface tension between the two faces. So if we have this mixture, those two beakers contain exactly the same composition. They contain 200 milliliters of oil and 800 milliliters of water. And in the nanoparticles, we form droplets that are 100 nanometer in diameter. So if without surfactant, maybe the surface tension, the interfacial tension between the two faces is 50 millinewton per meter, while with surfactant, the surfactant decreases the interfacial tension, it's much lower. What happened is that in the first beaker, the interfacial area is really small, but if we form a lot of very small droplets, the interfacial area increase in a very impressive way. And if we calculate the interfacial energy of those two systems, there's a big difference. It's much higher in the dispersed phase system than in the non-dispersed system, which means that there's a thermodynamic drive to lower the energy of the system by going back to the state instead of remaining into the dispersed phase system. However, if you add a surfactant, it lowers the surface tension. It lowers the surface tension of both cases. However, the thermodynamic drive to go back from the dispersed phase to the fully coalesced biphasic state is much lower in the case when you add surfactant than without surfactant. So we could consider the interfacial energy of the non-dispersed system to be almost zero. So the thermodynamic drive is 10 times bigger for the non-stabilized system. So by using the surfactant, we we don't necessarily reach the equilibrium state where this system would be more stable than this one, but we decrease the gradient of chemical potential that lead to breaking down the emulsion to form the coalesced system. Yes. So there's different kinds of surfactant. There's ionic surfactant. They are usually, I would say, the most efficient one. There's SDS, or sodium dodecyl sulfate, which is the go-to choice for any new mini emulsion. And then there's another one that is quite popular. It's acetylammonium bromide. And we could also use biologically derived compound like lecithin, because both sodium dodecyl sulfate and CTAB, they are in fact they are not very compatible with biological applications. So if we want to feed our nanoparticles to cells, we cannot really use those kinds of surfactant. And then there's also another class of surfactant that are non-ionic. It could be bridge or lutenzol, which are a mixture of a PEG segment that is hygrophilic, and then a polyethylene segment that is hydrophobic. Another frequent one would be tween, where we also have PEG base segment and very hydrophobic segment. And then by tuning the composition of those two segments, how long the hydrophobic tail is and how big the hydrophilic tail is, we could stabilize different emulsion. So when you do a mini-emulsion, usually the continuous phase will be the solvent in which the surfactant is the most soluble in. And then we could summarize. So we have two different functionalities that are tethered together, and this give the propensity, that explain the propensity of any surfactant to go to the interface. So in one phase, the one side of the molecule will be more solubilized, and in the other phase, the other end of the molecule will be more solubilized, which will bring the surfactant molecule just to the interface. And by populating the interface, it will decrease the interfacial tension between those two phases. And that's really the role of the surfactant molecules, is to decrease the interfacial tension. And depending on which surfactant you use, they are not really interchangeable. If you change the ionic surfactant the surfactant that you use, if you change the amount of surfactant that you use, you will get different emulsion. So what I mean here is 4 different surfactants. So we have SDS and we have CTAB. They behave more in a very similar way, because the critical micellar concentration for both are not that different, and the size of the micelle that it can form, it's also similar. However, when we move to polymer-based surfactant, it's a completely different story. So usually they have much higher CMC than smaller molecules, and they are also by themselves bigger, and they can form bigger vesicle. And that's what we observe, is that the diameter of the particles that we obtain using polymer-based surfactant are usually much bigger than what we observe with small molecules. And also what is really important is how much of surfactant you put in. The more surfactant you put in, the more new interface you could create that will be stabilized by the surfactant. So if you can create more surface, you could also stabilize more smaller particles, which explain the decrease in the size as you increase the surfactant concentration. There's 2 ways to increase the surfactant. In fact, it's not so much the surfactant concentration that is important, but the ratio of surfactant to monomer phase that you have. That's really the critical point. So you could use the same volume of water phase and oil phase and increase the amount of surfactant in the water phase to observe this phenomenon. Or you could also keep the surfactant concentration in the water phase constant, but decrease the amount of oil phase that you use. And that's usually the best way to go about really tuning the size of the nanodroplets that you form. So why the addition of surfactant prevent the coalescence of the nanodroplets? It's because there's different forces that are at play between in colloidal system. It's true for both nanodroplets and nanoparticles, by the way. So on one side, we have attractive van der Waals forces between particles or between droplets, and there's dispersive forces. So the Born forces are only observed mostly observed for particles. It's when 2 particles are closer than their diameter, they repel each other because they cannot enter each other, which is not the case for droplets because they will just merge. And then we have Coulombic repulsion if you have charges at the surface, and you have steric repulsion if you have long polymer chains, let's say, that are used to stabilize the particles. In most cases, it's usually more a combination of both Coulombic repulsion and steric repulsion, or sometimes called electrosteric repulsion, that is observed. But for simplicity, we'll treat both very independently. So if you have chargers, if you have two electrons, they cannot really collide because they will repel each other. When you have a charged surface, it's a little bit more complex because it's not two point charge, it's two charged surfaces. And those two charged surfaces could interact together. It could be summarized by the DLVO theory, which is from DLVO from those guys, two Russian guys and two Dutchmen that at the same time came up with the same explanation for the colloidal stability of charged particles. So on one hand, you could describe the van der Waals interaction between two particles as depending on the Hamaker constant, which depends on the system and the radius of the particles, but it's divided by the distance between the two charged surfaces. And the electrostatic potential is given by the electrostatic potential of the surface, which is a complex function of how many charges you have. And it decays exponentially with the distance between those two particles. So the total energy in the system between those two droplets could be summarized just by adding those two different forces. And what we observe is that as the distance between two particles decreases, the attractive van der Waals force increases. And as the two particles get closer, the electrostatic repulsion also increased. And the important thing is the balance between those two forces, where we could reach a state where there's more repulsion than there is attraction. And to reach this stage, you could try to tune the electrostatic potential of the surface by adding more charged species, by using more surfactant. So if you increase the charge of the surface, you also increase the electrostatic repulsion between those particles. So in this equation, we have a constant K. So you could be thinking, what is this K about? This K is about the concentration of ion in solution. So there's this concentration of salt, let's say, or of ionic species in solution that is also really important when you're talking about electrostatic repulsion. So as you increase let's say, the salt concentration in the system, you could see at some point collapse of your system. It won't be colloidally stable anymore, just because you're screening the effect of the electrostatic potential of the surface. So it's something that is really important to control when you do mini-emulsion. It's how much salt. It's not just salt. Here it's the addition of sodium chloride, but it's also the pH of your solution. It's any charged species that you have in solution. It will strongly influence the stability of your emulsion, and it's something that needs to be controlled. And sometimes just using millicube water from the out of the machine, it might not be enough. It might be better to use a buffer solution to have reproducible results, because depending on exactly how much CO2 from the air that will dissolve in your water, you will have different amount of charged species, and it will influence the colloidal stability, which will in turn influence the size of the nanodroplet that you form. When you use non-ionic surfactant, it's a little bit more complex. There's no good model to explain the steric repulsion, but it's basically the same. Those steric repulsion are due to the fact that if you have two corona of polymer chains that try to interdigitate, it reduces the entropy in this region, which is not thermodynamically favored, so it will usually repel and not interpenetrate. And also, as the local concentration of polymer increase, it will create an osmotic pressure, and solvent will be dragged to that region. So it will, if you have more solvent in this volume, it will also increase the distance between the two particles. So it's used as a buffer, so they cannot interdigitate. But to have this effect, you need to have the right concentration of chain. And here, for the ionic stabilization, the more you put, the better it is. When you're working with non-ionic surfactant, sometimes the more you put, it's not the better that it becomes. Because although the interdigitation is becoming smaller and smaller, the stability is also decreasing, because the stability in the sterically stabilized system is due to the solvation of the chains. And if you pack the chains too much, they are not as well solvated. They cannot reach their thermodynamically stable, most stable conformation with that is defined by the radius of gyration of the chain in the free chain. And if it's confined, if it feels this effect of confinement, you lose slowly any enthalpic gain that you could have by not interdigitating. So is the addition of a surfactant enough? So if I just mix water monomer and surfactant, my sample after one day doesn't look that great. The problem that we have to overcome now is called Oswald ripening. So it's due to the diffusion of the monomer through the osmotic, through the continuous phase. So the monomers are never completely insoluble in the continuous phase. Even when you use fluorinated monomers, it's still slightly soluble. It's an equilibrium. You don't need a high solubility to have problems with Oswald ripening. You just need 1 out of 1 million to be a little bit soluble to be able to diffuse, and it's the start of the problem. It's the start of the problem, especially when you have size distribution of particles or droplet, because the small particles will diffuse faster, and the size will reduce, and eventually they will completely merge. This is a problem that you, I'm sure, have experienced Oswald ripening in your life, because if you buy, let's say, ice cream and you leave it in your freezer for a long time, at some point you will see some ice crystal. Those ice crystals are already present at the beginning, but they are small and well dispersed in the continuous phase of cream around. But as you keep it in your freezer, the smaller ice crystal will dissolve and will recondense on the bigger one, and at the end you only have big ice crystal in the ice cream, and then the texture is completely ruined. It's the same thing for your emulsion. The problem is the Laplace pressure. So as the size of the particles decrease, the Laplace pressure of the system increases. So the existence of small droplets is less favored than the existence of bigger droplets. And it depends on the surface, the interfacial tension between the two faces. So either you need to decrease the interfacial tension to 0 to not have any effect of Laplace pressure, or you need to have infinitely big particles. That's the only two cases where you will have near to 0 Laplace pressure. If we have droplets of, let's say, styrene in water, the typical Laplace pressure that we experience with droplets of around 100 nanometer in size is something around 12 to 15 bars, which is a quite high pressure that could drive a lot of chemical phenomenon, and it will increase the solubility of the styrene in the continuous phase, and then there will be migration and formation of only big coalesced droplet. So how to fight Oswald ripening? We could add a osmotic pressure agent. So the osmotic pressure agent, sometimes it's called an hydrophobe or ultra-hydrophobe or a co-stabilizer. Ultra-hydrophobe, that's right when you do oil and water emulsion, but if you use water and oil emulsion at that time, you want to use ultra-phobe, or you want some ultra-hydrophile You want something to be very soluble in the droplet and very insoluble in the continuous phase. Usually, it doesn't need to be insoluble, because nothing is insoluble, but you want it to be much less soluble than the monomer. And those molecules will create an osmotic pressure. So the osmotic pressure, it's the pressure that is created from outside of one side of the compartment to the other, because here there is no Laplace osmotic pressure agent. So there's a drive to dissolve some more, to dilute the osmotic pressure agent. So for our droplet, what it will lead to is to try to reach a condition where the pressure in all the droplets is equal, since those molecules cannot dissolve or cannot be dispersed really in the continuous space around. So what is interesting here is to see that the osmotic pressure, it's a colligative properties. It means that it depends not on the amount in grams of hydrophobe that you dissolve in the dispersed phase, but it depends on the number of molecules that you have. So yes, long molecule, I don't know, Teflon is really not water soluble, but one molecule of Teflon will create the same effect as far as the osmotic pressure is than one smaller molecule. So it could be more interesting to add 2 weight% of an additive to the monomer phase that is of the lowest molecular weight possible. So we will increase as much as possible the osmotic pressure to counteract the effect of the Laplace pressure. But even in the best system that we could stabilize against Oswald ripening, if I go back to my favorite example of styrene and water, by adding hexadecane, we could create, by adding 2 weight% to styrene of hexadecane, we could create an osmotic pressure that is about 4 or 5 bars per particles, which is much lower than the Laplace pressure that we have in the system. So still, we are not at the really thermodynamic equilibrium where the Laplace pressure is equal to the osmotic pressure. We are just better than without any osmotic pressure agent. But we could use Oswald ripening. It's not just like something bad. We could use it to make more complex mixture. For example, if you need a bimodal system that is have a bimodal distribution, you could prepare 2 separate mini-emulsion of the same size that contain different concentration of osmotic pressure agent, and mix them together, and then we will observe diffusion of the from the droplets that have low concentration to the droplets that have high concentration. So those droplets that were made with a high concentration of osmotic pressure agent will grow, while the other one will decrease, and we will end up with a bimodal distribution of particles, which might be interesting or not, depending on what you want to do. So now, do we have a stable emulsion with our surfactant and our osmotic pressure agent? The answer is, well, not really. So if we wait to start the polymerization with our stabilized droplet, if we wait for a different time, we could see that there's a change in the size of the particles that we get. This is because there's still a little bit of diffusion going on, and it's not a, we are in a metastable system. We are not in a stable system per se. And so if we wait for a long time, we will see a change in the size of the nanoparticles that are formed. One way that we could play on that is to try to stabilize a little bit more the droplets after the emulsion. So the problem when you do mini-emulsion is that the amount of surfactant that you put in will influence the size of the nanoparticles that you get. But this concentration of surfactant is important just during the mini-emulsification itself, during ultrasonication, during the high pressure emulsification and so on. But once you have your stable emulsion, you could add more surfactant. And the addition of this surfactant after emulsification will decrease the interfacial tension. It will decrease, coincidentally, the Laplace pressure of the system. And if you're lucky enough and you use a good surfactant, you could reach a region, a place where the osmotic pressure created by the hydrophobe that you added to the monomer solution and the Laplace pressure would be stable. And then you really have a thermodynamic equilibrium, and you could wait forever to polymerize, and you will always get the same size. There will be no more evolution of size with the stored mini-emulsion. This is true to some extent. You will always have some coalescence just due to Brownian motion, and although we have the surfactant that should stabilize against two droplet merging, it's not perfectly efficient. So if you come back in a year from now, probably it will be different, but you could easily stabilize emulsion in this way for weeks and months. But the only way to really stabilize and stop any diffusion process in your system is to do the polymerization. Then nothing will change. But you could still have coagulation of particles after that. So in summary, Miniemulsion is super versatile. We could do all kinds of things, but the system is always metastable. We cannot do anything about it. It's the nature of the Miniemulsion itself. And because it's metastable, it could change over time. And the results that you get depends on everything. It depends on the volume of the two phases that you use, on the surfactant that you use. If you change monomer, it will also change the position of the equilibrium. If the temperature of the lab changes, change the position of the equilibrium. And the emulsification condition are also super important. In fact, everything is important, and you should note everything because you will see problem of reproducibility at some point. Working with Miniemulsion, it's always challenging to really have reproducible results because it depends. The stability of the droplets depends on so many parameters. So that's about it. I think it's, for me, the basic point of how to successfully do a Miniemulsion. If you have more questions, I would be happy to answer.